Hello, everyone. It's wonderful to be talking to you about what I love and passionately work on, quantum information and quantum computing. You've already had a brief introduction to quantum mechanics yesterday and a great introduction about the potential of quantum computing as well, including some research today. So what you'll see from me for the next couple of sessions is an introduction to the classical computer science perspective on quantum computing before we dive full into quantum computing. I'm Jibran, a member of QWorld, a faculty firm working on quantum information. I specialize in quantum non-locality and quantum contextuality, but anything having to do with quantum computing, I'm more than happy to look at. And so the title kind of describes the introductory session of the QBronze workshop content that we'll be working on for today. But before we dive into those kind of technical details, it's a reminder what the content for QBronze will be like and what you need to do in order to complete those requirements. Have 5 quizzes that are available on Canvas. You should be finishing at least all 5 of them with greater than a 50% score on them. Your average score should be greater than 70%. You have a deadline by July 25 for finishing them off. You don't need to worry about getting it right on the first try. You can go through the quizzes multiple times to make sure you can kind of reiterate your learning. Maybe you missed something, and so you can attempt the quizzes multiple times. Anytime during the session today you have a question, please fire off a question in the chat on Discord or on Zoom. I'm happy to respond right away. It's much better if this is interactive rather than just me talking into the abyss internet. Now, a key component that people kind of miss out on in terms of this workshop, even though it's the quizzes on Canvas that are the graded part for the purpose of completion of the workshop, the way to prepare for those quizzes to attempt programming notebook exercises that have been shared with you via the Jupyter notebooks that you can download from GitHub. That's what you should be working on in order to test your understanding of the content. So first you attempt those programming exercises on the QBronze programming notebooks, and then you attempt the Canvas quizzes. That's suggested model that you should be working with. And you've got multiple people to help you out with. In addition, great staff that's available. A couple of people who are directly QWorld mentors, their handle on Discord, they and their remote office hours as well. They should be on and off available in general as well. But these are the times they should be available on Discord for you to ask your questions. They should be able to answer your queries, maybe have a one-on-one session to help you out with the technical question that you're getting stuck on. I'll share these slides on Discord as well. And this should be these times should be posted separately as well, if you want to look them up later on. Something that was already very evident in the research talks that we already had is the diverse backgrounds that people have that are working on quantum computing in multiple different things. One of my favorite jokes sums it up as well. So it goes something like an engineer, a physicist, and a mathematician check into a hotel for the night. They all 3 of them get assigned a very identical room. They're tired after a long conference, so they turn in for the night, sleep right away. It just happens that the engineer's curtain catches fire during night. He gets up, sees the fire, goes to the washroom, fills a bucket with water, throws the water onto the fire goes out, all's well, goes back to sleep. It just happens that the fire now has gone over to the physicist's curtain in his room. The physicist gets up, sees the fire, goes to the washroom, sees there's a bucket, but there's also a water hose. Sits down, does a quick calculation to figure out what's the optimal angle to incline the water hose at that will minimize the time in which the fire goes out. Does that calculation, connects the water hose to a tap, turns it on, the fire goes out. Great. Physicist goes back. Now it just happens next, as you might have guessed already, the mathematician's curtain now catches fire. She gets up, sees the fire, goes into the washroom, sees the water bucket, sees the water hose, exclaims, multiple solutions exist, and goes back to while the fire keeps. Now, this isn't me picking on mathematicians in any way, but I think this kind of conveys nicely how different fields might have different perspectives. That's something I really love about quantum computing as well, where people with multiple different perspectives can be talking about really the same thing. So towards that end, we'd like to get kind of a classical computer science flavor of is quantum computing offering and what quantum mechanics is offering for computation. If people can just quickly shout out in chat, what would their favorite superpower be? I'll connect it to quantum computing soon, and some of you might already guess the answer, what I'm trying to link towards. But what's your favorite superpower? So Discord has Zuhair saying teleportation, Shor saying reading mind, time travel, flying, telepathy, flying, simulation, interesting. What exactly do you mean by mind control? So a lot of mind telepathy related invisibility, knowing everything at once, solving NP-hard problems. All right, someone is really, just doing classical computer science stuff. Knowledge, being in 2 places at once, time travel. All right, perfect understanding of quantum mechanics. I love the kind of quick responses. Speaking all languages, very interesting. Speaking all languages, flying, invisibility, future prediction. So just because it gets to kind of along the lines of what I want to get at is future prediction. What exactly might one mean by that? If you've been following some of the X-Men movies and whatnot, this is a superhero from comics and movies of X-Men. procrastination. So what's her? Control the flow of time for luck, right? So how would you now quantify mathematically luck? In some sense, kind of predicting what we want to go towards is that we want to gain ability to essentially manipulate probability or probabilities in general, right? So imagine the sample space of all possible things that ever happen. And now when you connect the dots, any mentioned superpower that we saw really is encapsulated within the sample space of all possible events that ever has happened or ever will happen. And so any possible superpower you might want, if you have the ability to tune or choose how the probability vector evolves, you basically just assign the probability to the component in this great big infinitely big sample space of all possible events to the thing or the power that you want, and that's what you have, right? So essentially you get the ability to gain all superpowers by just being able to manipulate probabilities over an infinitely large, right? So that's the one perspective on this. And what I'll try to convince you by the end of this first bunch of workshop related material in QBronze is, while quantum computing is not the full-fledged version of the power, it definitely is exactly along those lines where you kind of imagine classical probability, classical physics and classical theory of computation as allowing you a way to manipulate probability vectors. And then quantum computing and quantum physics comes along, and then you have essentially what you have is a richer way to manipulate a bunch of probabilities. So that's exactly along those lines of getting that superpower, right? So that's why someone might be really interested in having this superpower. So towards that end, let me set up the field in terms of my motivation coming into all of this from a classical computer science perspective. So if you're a high school physics student, at some point you are introduced to Newton's laws of motion as kind of sacrosanct classical laws of motion. If you, admittedly, computer science is a much nascent field, but if one were to ask for, hey, what's kind of a corresponding, bedrock foundational law for classical computing, I think most people would agree, especially computer scientists, that it would be something along the lines of the Church-Turing thesis. We won't necessarily go into kind of historical details, but it's kind of key idea that set in motion evolution of how classical computer science happened. The idea being that in the early 1910, 1920s, people thinking about building different computational devices for specific problems, the idea becoming that you can build one universal computational device for doing any kind of computation that you're interested in. And that might almost seem like a trivial observation to us today, given that we are all familiar with loading up a program that we're interested in on our laptop, on our desktop, on our mobile device. But admittedly, it was really something of a deep insight a century or so ago. So the idea being that you can have one fixed hardware, and that one piece of hardware can now be coded via an algorithm to really compute any kind of problem that you're interested in. And that was the key insight coming in from Alonzo Church and Alan Turing. That kind of got codified as the Church-Turing thesis. Any reasonable model of computation that one might imagine, based on, if you want to connect it today to physical principles as well, is going to be equivalent to what they call a standard Turing machine, which Turing proposed. And if you're thinking about Turing machine, again, rather than going into details, imagine a grade school child learning to add integers, learning to subtract numbers for the first. Usually you would think that they would have a sheet that is divided up into individual cells. And if they are learning how to add, let's say, 2-digit numbers, you will have kind of the units block, you'll have the tens block, and you'll take the first number and write the units digit and the units tens digit in the tens block. Same thing for the second number, and then do a calculation that, all right, I know how to add 2 single-digit integers in my mind, and then repeat this process for all the different columns, and I know how to add arbitrary large. So that's essentially exactly the Turing machine model, that you've got an unbounded tape, memory essentially, and you've got a finite set of rules in order to figure out how to manipulate the tape. And that's all that it is. That's the Turing machine model of computation. And the great insight is that that unbounded memory, along with the finite set of rules in terms of how to manipulate that tape, gets you all possible computation, all possible calculations that you can ever do. So that getting codified in terms of the Church-Turing thesis led into exactly what Scott Aronson likes to call as a lemma existence of the software industry. Because now that you had one fixed hardware, you can now say, all right, let me program an operating system for this hardware, let me program a game for this hardware, and so on and so forth. So the entire software industry as we know it today, it lends itself or owes itself to the Church-Turing thesis in terms of why it exists. Now, there has been kind of a strengthening of the Church-Turing thesis that has been proposed, known as the extended Church-Turing thesis. And the extended Church-Turing thesis kind of brings in the additional notion of efficiency. If you note in the standard Turing statement, you basically just say, I've got one model of computation, I've got another model of computation, I'm just saying one can simulate the other. So that's like saying, using an abacus, I can do any arbitrary computation that I could do on a standard modern today supercomputer. Admittedly, in principle, that's true, but for sure, for large computation, in principle, while it's possible, in practice, it just might not be possible because it will take perhaps longer than the lifetime of the universe to do that computation using an abacus. And so the extended Church-Turing thesis formalizes slightly stronger statement saying that it's not just that any reasonable model of computation is equivalent to another, it's that every reasonable model of computation can be efficiently simulated by another, right? So it's kind of saying that if you take polynomial time to solve a problem in one model, you will still take polynomial time in another model to solve. It won't be the case that in one model you solve the problem in polynomial time, and in another model you will solve the problem in exponential. And for people who are not coming from a computer science background, the big two time slots that we're interested in as a kind of a big granularity on a big granularity level is polynomial runtime of my algorithm, essentially the time it takes for my problem to be solved, and exponential. If my algorithm has exponential runtime, that means that I don't really expect the algorithm to be solving any realistic input size problems because it will just take too long. So ideally, I want my algorithm to have polynomial runtime. Naturally, the smaller the polynomial, the better, right? If I can get it linear, I can get it logarithmic, even better. But kind of at an introductory level, computer scientists would like to think polynomial runtime, good, exponential runtime, not good, bad. And so what the extended Church-Turing thesis is essentially saying is that you take an algorithm in any single model, in any single platform, and you can then transform it into an algorithm for the other platform using this polynomial conversion. Efficient, as I mentioned, in kind of a big granularity for us right now would mean polynomial efficient, exponential inefficient. Naturally, you can fine-tune it more, but for our current purpose, this is sufficient. That we think of any algorithm, any problem that can be solved in polynomial runtime as having an efficient solution, and anything that is exponential or larger has been inefficient, right? So here you're pointing out a valid thing. What if my polynomial has a really large, and those are exactly the things people would be interested in when you do the fine-tune details. If you're interested, there's a blog post that I can post later as well that discusses exactly why it is that in practice, it just happens that whenever a problem does have a polynomial runtime, in practice, it just always happens that the constants in the exponent are small. We don't really have any interesting problem that has a polynomial runtime with 100 in the exponent or something like that, right? And reasonable is exactly along the lines that I'm not taking my computer and saying that the first model will be the first step of my computation, let's say, will take 1 second. The second computational step will take half a second. The third step will take a quarter second, and so on and so forth. Hopefully you get the drift. So if you make up arbitrary models like that, where somehow you are forcing infinite amount of computation in a finite amount of time or memory, those become unreasonable. With a slight variation, you can think of reasonable as well as what can be built physically. There's a slight caveat there, but we can discuss it on this. Hopefully that will. So are these states generalized? How can you define a Turing? So I'll post a link to a technical definition of a Turing machine, but think about the Turing machine as essentially your computer. So every computer that we have today is essentially a realization of the in-principle notion of a Turing machine. The only technical distinction would be in any computer that we have, there's always a finite amount of memory, whereas the Turing machine model of computation says that let's imagine that our computational device has unbounded. Yeah, the example that I gave you is exactly a converging series, but then you're essentially saying that in a finite amount of time, my computer would be doing an infinite amount of beneath, right? So those kind of weird models would be unreasonable because they won't correspond to physical models of computation. Very soon, if your computer is essentially halving its runtime for each next step of computation, very soon it will essentially create a black hole around itself because of the amount of energy it will need to be so fast in its process. I'll link also to Scott Harrison's blog notes that very nicely have a discussion in introductory level on this material. But hopefully the big idea is clear. The big notion was that the computers that we have today work on this notion of that there's one fixed hardware, and then you can have any kind of piece of software loaded on it to solve the computing problem that I'm interested in. And within this, there's a hierarchy of standard in principle equivalence versus efficient. And for the purpose of quantum computing moving forward, what we're interested in is this extended Church-Turing thesis, because in 1994, peaked classical computer scientists' interest in this was Peter Shor's kind of result that showed this problem of integer factorization. Give you an integer n and ask you to find its prime factors. The problem is not known to be solvable efficiently using a classical computer. And so what I'll emphasize here is not known. We don't have a proof, and that's something that sometimes gets missed in modern popular discussions of quantum computing and strengths of quantum computing. So while Shor's algorithm is one of the strongest examples that we have of strength of quantum computing, there is kind of a slight nuance. We so far do not know of any classical algorithm that will solve the problem of integer factorization efficiently. It may happen tomorrow that someone proves that no such algorithm can exist. It may also happen tomorrow that one of you, let's say, proves that, hey, here's an efficient algorithm for integer factorization on a classical computer. Both possibilities are open, given that lots of smart people have tried it over the last multiple decades. Kind of the folklore kind of understanding is that, yes, it probably is not possible, but we don't have a proof. What Peter Shor did, though, is provided a counterexample to the extended Church-Turing thesis, where he essentially proved that if you forget about classical computing for a minute and imagine that you had a quantum computer, then on a quantum computer, there exists an algorithm, actually the one he proposed, that would solve the problem of integer factorization in polynomial. And so now, if tomorrow we were to prove that integer factorization cannot be done efficiently in a classical computer, this would falsify the extended Church-Turing thesis, because then we would have this separation between classical computers that can only solve integer factorization exponentially versus quantum that can do it efficiently. Is RSA extensively used today? It is still extensively used today for encryption. So integer factorization was important. People who don't know, it is one of the building blocks in many encryption schemes, such as RSA. It's used in public cryptography. So whenever you're doing online transactions, buying something online, chances are in the background, your vendor, your website is using the RSA algorithm to keep you secure. What a polynomial time algorithm for integer factorization would give someone an ability to do is to hack or break that encryption, and then your data doesn't remain secure anymore, right? So that's the modern 5-minute spiel of why quantum computers, strengths, or why quantum computing might be more strong and more powerful than classical computing. So the von Neumann architecture is something more coming in from kind of a practical application design, digital design kind of perspective, as the Turing model is more kind of a theoretical model for the purpose of algorithm design and theoretical modeling, right? So there is a distance. But naturally, the idea would be that a Turing machine model is equivalent to the von Neumann architecture. Are there computing systems that cannot be simulated by a Turing machine? There is no, again, quote unquote, reasonable model of computation that cannot be simulated by a Turing machine. We can talk in detail on Discord later on about what those unreasonable, one of them I already. All right. So then this is the motivation argument from a classical computer science. Lots of classical computer science departments got interest in quantum computing exactly when Shor's result was popularized. And so now what we'll get into is building a foundational framework for talking about classical information, classical computation, and by end of today and start of tomorrow, getting to formalizing and representing quantum information and quantum computing. So this will be an abstraction from physical detail. That's kind of, depending on your perspective, one of the benefits or disadvantages of being a theoretical computer scientist, right? So you're abstracting away from the physical details. In much of the talk that follows now, I won't worry about what my underlying physics system is. Is it photon and I'm interested in its polarization, or is it an electron, or am I talking spins or any other stuff? For example, yesterday you were introduced to the simple harmonic oscillator. So I won't necessarily be interested in talking about the details, actual physical system, but rather talking about my ability to represent and process information using a physical system, abstracting away from its physical details. So I have a physical device, let's call it a physical device X, and what I'm interested in thinking about is that this physical device is some number of, naturally it doesn't help me if that set of states is empty, and for the purpose of our discussion today, we won't be interested in a physical device having infinitely many possible states. So for the purpose of today, let's imagine my physical device X can be in some finitely many different set of states. Naturally, kind of for the purpose of computation, the standard one you might imagine is, hey, my set of states is, say, represented by just a set 0, 1. And so the usual notation over here would be I represent the symbol capital sigma to represent that set that represents the set of different states that my device can be in. 0 and 1 here naturally are just labeled. I might as well also just choose H and T. Some might take it for head and tails for a coin flip. That's perfectly fine as well. I can take it to mean A and O for apples and oranges, or anything you might like or takes your fancy. They need not be 2 labels as well, right? I could have a go 0, 1, 2, 3, or 4, 5, 6, or whatever. So the idea is just that I have a label that allows me to identify unique, finitely many set states of this physical device. Now, Now, my question to you is, imagine if I just have a physical device with this sigma as its possible set of states. How can I codify and code the different ways in how the system can change? Right? So if my physical device can only be in state 0 or a state 1, it says 4, everyone agrees. Maybe shout out on chat, what those 4 different methods would be. Electric, so I'm not talking about the physical details things. I'm more like, I've got my physical device X. It could be in state 0, it could be in state 1. And now it will undergo a change. In how many different ways could I make my system, my physical device X, undergo this? So N being, I assume, the answers on Discord 2. Right, so the usual way one might imagine is, all right, so I have my physical device X. It can be in state 0 or state 1. And now one way it can undergo a change is to basically say, and people might write it in different ways. One might be to say, hey, all right, my system undergoes a change now such that it will always become in the state 0. So regardless of whether it started out in state 0 or 1, it will now always. Another possibility might be that no, it will now all undergo an identity change, i.e. if it was 0, it will remain 0. If it was 1, it will remain 1. Or it could go in through kind of a flip operation. The 0 becomes 1, the 1 becomes 0. And it might be that it becomes 1, 1. The state always becomes, right? So if you think about it a little bit and imagine, systems going through this kind of change, you'll agree that these are the 4 different possibilities, deterministic possibilities of my physical device X undergoing a change. I might even label it as my kind of function F0, F1, F2, F3. I can think of these functions F as basically a mapping from single, let's say, to another single bit, right? Each of these F encode these single bits, single Boolean functions encoding a single bit that take a single bit as and output a single bit as well. As some of you have already been shouting out, all right, the number of functions are kind of 2 to the n or 2 to the n. Let's get it soon to exactly this counting argument. First, by what if now I had 2 physical devices X? So I had 2 identical physical devices X. The number of different states that it can be in now are also 4 through a slightly different kind of way of representation, right? I could now represent it as my system can be in 0, 0, 0, 1 state, 1, 0 state, 1, 1. And this I'll represent as sigma 2. So this would be, if I had 2 device X, right? Then their states could be represented as 0, 0, 0, 1, 1, 0, 1, 1. And so if I have n such devices, as people have already shouted out, the number of different states will be 2 to the n. Agreed? Now, this too is slightly different than my earlier question for the ways the system can change. So over here, we saw that even if I had a single bit, there were 4 ways in which the system could change, right? So what if now I have n bits? How many ways would the system change? There's one answer already. There's a second option, different than the one on Discord. So there's 2 to the n, there's 4 to the n. So I'm thinking in terms of n, right? So the question is, how many Boolean functions are there on n bits? So a couple of n to the n's. Let's try to work out. So my input would be this, right? X1, X2, all the way up till Xn. Imagine writing down the truth table, just like we did above. It would be represented by a function of X1, X2 up to X to the n, right? And I would have, as we just discussed over here, 2 to the n different entries or rows in this table. Now, choosing a single function means I just fix all of the entries or a single column over here, which means I need to fix 2 to the n different entries. But that's just fixing a single function f, right? I'm asking how many different functions there are. Just like over here, this was just a single function f. There was also this, also this, also this. Well, it's exactly the argument, the reasoning that you might have used to come up with this 2 to the n. What was the reasoning over here? The reasoning over here, there are n buckets kind of, right? 1, 2, 3, up till n buckets, and each one has 2 options, and so you got the answer 2 to the n. But now the number of buckets that I have are already sized 2 to the n. 1, 2, 3, 4, all the way up till 2 to the n. And each of those buckets has 2 possibilities, so it will be 2 to the 2 to the n. So it's kind of a super exponential. It's not 2 to the power 2 times n or like that. It's 2 to the power 2 to the power n. So it's something really beyond the exponential kind of class as well. It's a super it goes one level above kind of the exponential hierarchy. And kind of a nice pointer now is to know that this is exactly why the class or the problems in machine learning are really extremely difficult to think about, even in terms of or get analytical results for machine learning. Because what it is, machine learning is nothing more than identifying or classifying a class of function. If we thought that looking for a row 2 to the n size number of rows is already a hard task, for sure looking for a function in this space of 2 to the n number of functions is much harder on n functions. So right, so you agree that over here in this table over here there are 2 to the n, say equal to capital N number of rows. Agree? And now if I want to single choice of a function, then I have to choose a 0 or a 1 value for each of these individual entries in this 2 to the n size long column. So if I just choose a 0 here, a 1 here, a 0 here, a 1 here, and so on and so forth, I've just fixed one function. Any choice of such a column vector fixes one function. Now the issue or the problem just becomes me counting how many different such functions can there be. And so you're just counting 2 options here, 2 options here, 2 options here, and so on and so forth. How many times will you multiply 2? Well, you multiply them capital N number of times. So it will become 2 to the power capital N. Capital N is equal to 2 to the n, small n. So that becomes 2 to the power 2 to the power small n. So we're not at all at the moment talking about qubits, right? We are just talking about classical bits and classical information. And one of the reasons for focusing on classical information and classical bits is exactly to help us later on identify where exactly is quantum computing differing from classical computing. Lots of times it will get easily thrown around that in comparison to classical information, quantum information allows you to do exponentially many things in some weird kind of way. We'll formalize that hopefully by tomorrow. But the thing to emphasize and note here is that, we are already running into exponential possibilities in terms of what we can represent with n number of bits as well, right? So if I have n bits, I can present 2 to the n many things. It's so it's exactly, to answer Buttercutter on Discord, it's exactly the option that we have of choosing 2 possible entries for each individual row in the column for the function that gives us this 2 to the power 2 to the n. So I want you to just keep this at the back of your mind as you move towards computing, and we'll contrast this later on with what exactly is something uniquely quantum feature versus something that we already had in classical computing. All right. Now, if you note, everything that we've discussed on this slide was kind of with perfect information, with certainty of knowledge. Everything was deterministic. If I have this thing as input, and if I know my function, that I know certainly what my output. But naturally, in real life, things are not certain. And so we have incomplete information in terms of the physical device that we might be interacting, and so on and so forth. And the usual thing that we use to represent lack of would be, so now that's an excellent question in terms of n bits getting mapped to m bits. I'll leave that as an exercise for you. Try to figure it out in Scott, and we can discuss it. Example so Jerry's asking, solving the example for 10 bits. So for 10 bits, you'll have 2 to the 10 number of possibility for the input string. So you'll have x1 to all the way up till xn. And then you're fixing up, x10, sorry. And then you'll be fixing a function which will go from, which I'll have rows going from all the way 0, 0, 0 till 1, 1, 1, 1, 1. The number of rows here will be 2 to the 10. And then I'll be fixing all the entries over here, and that will fix one function. Some f sub I will be fixed. This I, in fact, you can think of, take this entire binary sequence that exists in this column and take that binary sequence and convert it into its decimal representation. And that will be this index I. How many different values will this index I take? There will be exactly 2 to the power 2 to the power 10. So I'll move forward from here. If there are questions on this, I'll take it up on this. Note that right now, I don't necessarily need to represent the function as a matrix. We can, and we'll do it soon. But you can think of this as this mapping. Going back to the question, how do I represent how do I reflect incomplete information in my representation? Fixing a function overall would be fixing kind of those entries in the column, right? So over here, when I am saying f sub I haven't really specified all the entries over here, right? So for example, for a single function, over here, this fixing 2 zeros was me fixing the function to be f naught. That the input 0 gets mapped to 0, then 1 also gets to 0. And so here, as we've discussed already, for incomplete information, the natural mathematical tool that we use is probability. So let's bring it up into our formalism. Each column on the left have n possibilities. No, in my formulation over here, each column on the, so rather than thinking about a column, think about a row. What I fix in a row is basically saying a fixed entry for each of my physical devices, 1 up to n. I fix a single value for my bit. It could either be a 0 or a 1, it could be a 0 or 1, and so on and so forth. So in a single row, I have a bit value for each of the n bits for the n physical devices, and I can then do so forth in 2 to the n possible ways. Let's move on. So incomplete information can be represented via probability. So rather than knowing for sure that my system is in state 0 or state 1, I would have a statement of the form that I know that the probability with which state of my physical device is 0 is equal to, let's say, probability P. And the probability, if that's the case, that to be state for the system X to be in state 0 is P, then obviously for it to be in state 1, assuming only 2 possible states would be 1, right? Again, here, what I'll emphasize and be able to contrast it later. Now, if I imagine this as representing, let's say, a physical coin flip, right? It may not be a fair coin. It might be a biased coin with some bias P, where P is not necessarily equal to half. Naturally, P equals to half will give you a fair coin. I can take this P1 minus P and now represent it as a vector. So I've got a vector of 2 entries, P1 minus P. I can think of this as my state 0, the probability to be in state 0, the probability to be in state 1, or it could be probability to come up heads, probability to come up tails, anything, right? So the label depends on the experiment that I'm doing, the physical representation, the physics experiment that I'm doing. The mathematical detail in terms of the uncertainty would just be, all right, I did the experiment, and the physical device will be in state 0 with probability P, will be in state 1 with probability 1 minus. Now, when I do such an experiment, let's say I do a coin, do I actually see the probability P, or do I see the probability 1 minus? I flipped a coin. What do I see? If I'm the results, excellent. If it was a coin flip, the outcome would be represented by, let's say, a head or a tail, right? The outcome. The outcome for a coin flip would be just a head or tail. No need to worry about collapse state at the moment. We're just talking about classical information still so far, right? Either one of the outcomes. And so that, again, is something to remember. Trivial already. So when we look at this physical device X, we are not going to see the vector V, right? We are not going to either see probability P, but rather what we'll just see is one of the labels, right, of the state of so some element of the labels that I'd chosen right in the beginning, that my system can be in some set of states. That set of states we call sigma. And so one of those labels states is what you'll see with probability what? Probability exactly V sub, right? So in this case, probability to see the state 0 is V naught, V sub 0, so P, and V sub 1 is 1 minus. It won't necessarily be 50%. That depends on what the value of P is. If P is half, you get 50%. But just the emphasis that the outcome of this experiment is the label of kind of a set of states. It's not the probability, it's not the vector V, but rather just the label from the set of states. That label comes, if we were to repeat this experiment multiple times, with the corresponding probability V sub sigma. So that's a setup that we already have in classical probabilistic information, right? So again, if I have P1 minus P as representing my level of knowledge about a classical system, I could, for example, now apply this transformation to what's the result of this calculation. So we get a row from the table you showed. No, so not exactly. From our first slide discussion over here was about perfect information, right? So if you know the input and you know the function, then you also with certainty know what the output. The whole point with incomplete information is that we don't necessarily know with certainty what outcome will be. We can just say certain probability the output will be this, with certain probability the output will be something else, and so on. So the outcome naturally will be one of the labels from the set of with a certain probability, right? Now in this case, for example, what have we attained? We have attained kind of a flipping of the probability, right? And so this kind of suggests now that the transformations that we would do on our classical information with incomplete knowledge or incomplete information would be naturally represented by matrices. Previously, in the first slide, when we had perfect knowledge, our information was represented just by a bit, and it sufficed to think about Boolean functions to do the mapping with certainty. Now, when our information is represented by a probability vector, then the transformation for that probability vector would be by this would represent kind of a flip of the bias. This transformation itself is not doing any normalization. For sure, it's normalized, right? So you can think of this transformation in multiple different ways. One way to think about it in the way on is kind of a flip operation or negation operation. We'll have occasion later on to also think about how to think about them geometrically as well as different transformations corresponding to rotations and deflection. In this case, this is just representing the fact that I have applied a certain vector. Initially, my information about my physical device had this property that when I would observe it, I would get the label 0 with probability P, and I'll get the label 1 with probability 1 minus P. But if my device undergoes the transformation corresponding to this matrix, I'm not sure what the physical process was, what that corresponding to that transformation. I'm just saying that this is a mathematical representation of the transformation. Then that would correspond to flipping the bias. Think of P as the bias, right? So the probability P is the bias. If P is equal to half, then there is no bias. It's kind of an unbiased coin. But for any for cases when P is not equal to half, coin that you. So similar to kind of the perfect case, you can ask the question, all right, how can I write down the different transformations that can happen? And for the moment, let's imagine my transformations to be still deterministic. So if I were to write down these 4 transformations that that I can do on a single perfect bit of knowledge, what would that look like on a 2-dimensional probability vector? So for people people have queries about the matrix transformation, let's work through this slide. This will exactly hopefully help out in kind of understanding that transformations. So if I take those 4 transformations and write them down as matrices, they'll still correspond actually to deterministic operations. But rather than thinking about as Boolean functions, I can think of them as now matrices. So one matrix may be written as, imagine that the labels for the columns and the rows are heads. So based on this matrix, what kind of transformation is this matrix going to apply to an arbitrary vector of the form P1 minus P? What will be the output vector? Heads, right? So this will output 1, 0. So in other words, I will always heads. The transformation over here in this case earlier on, let's say if I make 0 as representation of heads, then this Boolean function that said, hey, 0 will be mapped to 0 and 1 will be mapped to 0. In the case of a transformation over probabilistic systems or over this vector P1 minus P, that transformation would look like. Very similarly, the identity transformation, as one might already imagine, would look like the identity matrix. The flip operation would look like exactly what we did in the previous slide. This is the flip or the negation operation. And then finally, A3 will be, so this one will be the one giving you always tails, right? Agreed? So now, but these are just deterministic transformations. What about, if the transformation itself is also probabilistic? One nice way to write them down is you can just say, hey, probabilistic transformation B, right? The ways my state of the system can change or evolve is now being represented by transformations or matrices. So an arbitrary probabilistic operation then for a single bit could be written as, right? So I'm just saying, hey, all right, I flipped a 4-sided, so it can come up 0, 1, 2, 3. P naught is the probability with which I will apply A naught. P1 is the probability with which I'll apply A1 and so forth. So any transformation that or any 2x2 matrix that I can break or decompose into this form or write in this form would then correspond to a transformation that I could apply on a single piece of probabilistic bit. So we started out with a classical deterministic bit. We generalized that to the notion of a probabilist. And now we have the notion of a probabilistic operation on a probabilist. So in this case, one example might be breaking up half A1 plus half A2. What would this look like? Rashid will talk about generalizing transform, especially naturally, that's what we do in quantum for sure as well, right? But for our current example, right? So this would be just half everywhere, scalar multiple out. This would be half outside and 1 everywhere inside. Sigma P sub I over here should equal 1. Sigma I P sub I equals 1. So here, what would this represent? This would represent fake coin. So I'd say, hey, half of the time flip the coin and half of the time don't flip the coin, right? So this would correspond to the transformation for a fake coin flip. So let's build on this to do a specific example. So the final operation will be the summation of all these matrices. So let me write down kind of a specific protocol that someone might do, and I'll ask you to figure out what the matrix for that would look like. So let's say we have a coin and we flip a coin which has representation given by PQ. The protocol then I follow is that I will flip a coin and based on the result, I'll do the following. We get a head, flip again. If we get a tail, turn over coin to head, right? So I'll explain this again. What this protocol is saying, this protocol is saying I've got a coin. I don't necessarily know the value of P, but I just know it's represented by PQ. And I'm just doing this once. I'm not saying keep doing this again. I'm just saying, all right, you flip the coin once, you see the result, and then condition on the result. If the result of the coin flip was a head, you flip the coin again. And if the result of the coin flip was a tail, you actually deterministically flip the coin over to a head. So that's all the protocol doing. I'm not saying now keep repeating this process infinitely. I'm just do this operation where I flip the coin first, so it has come up heads or tail already. So so I've got my device, it's either in the state head or tails with probability P and Q correspondingly. And then I'm saying if the state is a head, then flip the coin again. And if the state is a tail, then turn the coin over to a head. These two requirements, I want you to encode that as a matrix transformation. What would that matrix look like? So this would be a 2x2 matrix. There exist other ways to think about exactly the same issue about what are the class of probabilistic operations that can be applied, which end up being equivalent right after this. It shouldn't have negative entry anywhere, given that we're thinking about the entries as probabilities, and then certain normalization condition would also apply, and we'll fix exactly those after working through this example. So the question is, so these two lines in blue encode a certain transformation. It's a certain operation that I'm doing on my given. I want to now encode this operation in my 2x2 matrix representation. What would that 2x2 matrix look like? And so you can already start thinking about it in this way, where you say, all right, I know I've got to write down a 2x2. Let's imagine its entries are labeled by tail, head. One thing to kind of observe then is, well, what exactly is the meaning of the entry over here in this matrix? Given that we have fixed this tail head labeling of this 2x2 matrix, note that this entry would correspond to saying given head, given tails, it gives or represents the probability to transition to other state. In this scale, that other state is tail. That's the row case, right? So in this case, that would mean, so this entry, the second entry over here, would correspond to, given that I'm in tail, the probability to transition to a head. Over here, given that I'm in head, the probability to a transition. And over here, given that I'm in a head, the probability to transition to a head, right? So you see, the column labels is providing the conditioning, while the row labels is providing what I will transition to. Once these two are fixed, then I just need to go back to my description of the protocol to figure out what you can take, so the labeling over here is exactly tails, heads. So let's work through this. We get a head. So we are conditioning our column, we are fixing our column entry. So if we get a head, then flip again. Flip again means that we have just flipped the coin. Well, what's the probability to comes up a tail and a head? That's exactly this vector PQ. So the entries over here will be exactly this P black. The entries over here will be PQ. Right. So what was the reasoning we just used? If we get a head, i.e., that's my column entry, then flip again. Flip again means that I flip a coin, and this is the probability with which it comes up a heads, and this is the probability with which it comes up tails. I put down exactly that column vector as the column vector under the head label. If I get a tail, then turn over the coin to a head. That means deterministically, or I know with certainty that if the coin was in the state tail, by me deterministically turning it over into a head, with probability 1, it will be in the state head. So that means in this case, there's a 1 entry over here, a 0 entry. So my matrix is 0P, 1. Now, I can figure out what the net effect of this transformation is. To say, all right, if I were to take my coin flip and apply it to PQ, just to matrix vector multiplication to figure out my new result vector. So that means this transformation takes my vector PQ, and you can verify the calculation that transforms into PQ P plus Q square if I got it correctly. Right. So this protocol that I have takes the original coin with labels PQ, with probability PQ, and transforms it into this, transforms the probabilities into these new probabilities. It's a convention that we are fixing the initial event in the columns, the rows to be the transition. You can for sure flip it around. Still confused about flip again part? Flip again part means you have that coin, and if you flip it again, what's the probability it comes up tails? Well, the column vector tells you it's P. What's the probability it will comes up head? The problem. Okay. Now, as some of you have already mentioned, what are the ways I can generalize or think about these probabilistic matrices? If you note that this is the way we are thinking about these transformation matrices, then each entry is representing a probability to transition from a certain state to a certain state. So the standard constraint for probabilities would apply that all the entries, each individual entry in this matrix is strictly greater than or equal to 0. And each column vector now is representing a probability vector. The sum of the column entries has to equal 1. And so these two conditions also identify the class of transformation that can be applied on, in general, for any kind of classical information, the class of probability transformations. So what are those restrictions? Let's write them down. In general, square matrix is a valid classical transformation if it satisfies these two conditions, if and only if: 1, all entries are greater than or equal to 0, and 2, sum of all entries equals 1, sum of all column entries. And so these two conditions together define a class of matrices that are called stochastic matrices in the literature, and that's another way to. One of the research talks talked about Markov chains. Markov chains are used exactly to think about certain experiments and models. It's called finite. Right? This is for a single bit, but the same idea will come to that. So as someone is already asking about, is this for a single bit? Our representation so far is for a single bit, but the constraints that we have identified actually are just not for just these two constraints. For any kind of n by n matrix would be a valid transformation, assuming you have a physical device that has the corresponding number of states. Okay, so what if I did have multiple devices now and I had incomplete information about them? How do I join together the information about multiple devices? For perfect information, I kind of already saw this computation right in the beginning, where I kind of computed this set sigma 2. Well, now I've got kind of two different probability vectors. They may be identical probability vectors, but still two different, right? So I could have a coin x1 represented by PQ, and I have another coin x2, and let's say it has different entries RS. Now, if I wanted to talk about the two coin flips together, or the state of the two coins together, naturally in terms of the labels, I would have going from head, heads, heads, tails, tail, heads, tail, tail. But how do I combine the four probabilities together? Standard enough to do the calculation, right? So imagine if the labeling was head, tails, and I asked, well, what's the probability for the two coins to be in the state head, you will just multiply P with R and probability P times R, and so on and so forth. There are 4 different possible states in the sample space. So there are 4 different probabilities that you'll need to keep track of. Let's just write down those 4 probabilities as a single vector. What you'll get is exactly this tensor product definition of how to combine these two, right? So you take this vector PQ, you take its tensor product with the vector RS, you get something that's like PR, PS, QR, QS. So you've got now, so this would be, let's say, did I label it head, head? Yeah. So this would be probability for head, heads. This is head, tails, tails, heads, tail, tail. Note we already said in the first slide discussion that there are 2 to the n possibilities. So over here, given that both the coins had 2 states, the net number of possibilities here end up being 2 to the power 2, 4. This exponential increase in the dimension is again something completely classical, nothing to do with quantum. Note that each of these entries are probabilities, right? Remember, these were probability. They're not real entries. These are stricter entries, right? They are just entries that are strictly greater than or equal or greater than equal to 0 and less than equal to 1. And sum of P and Q equals 1 and sum of R and S equals 1 because they're probability vectors. Here, one thing to note is not all valid 4-dimensional probability vectors can be represented by tensor product of, let's say, I call this V1 and V2. And this is something that's nice to observe as well. So right now, again, we're not talking about the quantum at all, right? So entanglement, etc., all will come given our time today, maybe tomorrow. So we are talking about 2 classical coin flips. This has nothing to do with entanglement. We already have this nice feature, right? That's standard from your introduction to probability theory, that if you've got kind of these 2, if you want to think of them as random variables that represent the state of x1 and the state of x2, then for sure you can kind of combine them out together in terms of a tensor product. But you could also have a 4-dimensional probability vector, have a probability distribution over it, and it would be the case that the probability vector over 4 dimensions cannot be decomposed into 2 probability vectors of dimension 2. For example, the vector half 1, 0, 0, 1 cannot be written in the form PR, PS, QR, QS, which itself came from this representation. So already classically, we do have these notions that you have one physical system being a larger physical system, let's say, which is represented by this one, not admitting a physical or even a mathematical decomposition in terms of 2 smaller physical, right? And we'll compare and contrast this when we get to quantum entanglement. So just keep at the back of your mind this decomposition or the lack of this decomposition there do exist indeed larger vectors, probability vectors, cannot be decomposed into smaller probabilities. In this case, this happens to be a probability vector that's describing a perfection for sure. You could similarly have another anti-correlated vector, and that also admits similar issues. And the point is that sometimes these kind of correlations will be these vectors or the correlations resulting from these vectors to define or behavior when that's not actually the case. So we'll have to take that into account. Final thing for today, before we wrap up, we talked about combining multiple devices together to represent the physical system. What about the transformation corresponding to those systems? So for those transformation, let's say I've got a transformation A on a single coin and a transformation B on another coin. It's a tensor product between those 2 matrices, as one might imagine, given a previous discussion. So we'll just have this as a matrix for A, this as a matrix for B, and then that transformation also is this nicer, bigger transformation that you could write in this. So note that this will be a 4x4 matrix rather than a 2x2 matrix. Now, one example of such a transformation, again, completely classical, would be this is a valid 4x4 transformation, given the rules that we identified in the slides. It satisfies both of them. All of the entries are greater than or equal to 0. The sum of the columns equals 1 because there is exactly one entry in each column. It is a valid matrix. Could someone give me intuition about what kind of transformation what is achieved by this transformation? People who know it from the computation already know it as a C0. What exactly is a C0? It's not something uniquely or necessarily quantum. It's basically just saying treat. So you can think about the labels over here, right? So label the column and the heads again. So think of it as 0, 0, 0, 1, 0, 1, 1. They will be mapped to 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. Now, what's happening on the first block diagonal? Note that this is essentially the identity matrix. So we are essentially saying whenever the first 0, nothing actually happens because it's the identity matrix. However, when the first bit is 1, then the corresponding matrix is not matrix. So it's actually flipping the second bit. You can think of it as an XOR operation being applied on the second bit, but not always applying XOR on the second qubit. The XOR is applied when the first qubit is 1. Hence the name C0 or controlled not in this representation. The first bit is the controlled bit, and the second bit is the bit on which the not operation is applied. I recommended you work it out. You'll see this in the programming example as well. I'll finish up with the technical content as well, and I'll end with kind of a question for people to ponder over. Assume you have a coin, P1 minus P, such that you know that P is not equal to 0, P is not equal to half. Using this, how can you simulate a fair coin? We don't know the value of P, we just know that it's not 0, so it's not kind of a deterministic bit, and we know it's not equal to half, so we know it's not already a fair coin. You could think of those matrices as kernel maps as well coming on, but the way we are usually thinking about in our discussions would be also in terms of these mappings, where input is being transitioned to a certain output. But yeah, that's exactly something that kernel maps achieve as well. But kernel maps are also being used for simplification of those transformations as well, right? We won't off a certain digital circuit. We won't necessarily have purpose right now to talk about the simplification process, but just rather talk about what is the operation being applied. So the challenge question for people, incomplete information. So to finish off for today, the question for people to think over, Scott, I won't give the answer off right away, is assume you have, let's say you kind of are about to play a game where you need to make a choice who gets to go first, and you decide you will do it with a coin flip. You don't trust your friend that you're playing with. They may have a biased coin, so you now need to come up with a protocol that will guarantee a fair coin. You don't know that they have a fair coin. You are kind of assumed that they have a biased coin. So you want to come up with a protocol through which you guarantee that you have achieved a fair coin flip, given that let's say the coin's bias is P, and P is not equal to half, so you know it's already a fair coin. What protocol can you follow, or can specify the two of you and your friend should follow, such that it will achieve a fair coin flip result? I'm not sure whether some of the comments are answer to this question or something else. For answers to this question, I recommend people post on Discord, and we'll take them up perhaps tomorrow, or maybe even later, because I'd like people to think about it. If everything here is okay, then I'll quickly go and do a review of the programming notebooks that you need to do. They're essentially a review of what we've discussed today. Given how the time worked out, we won't have time to actually go through the details of those notebooks, but everything that we discussed today is discussed in detail in the notebooks as well. But any question before we do that? You can flip the coin multiple times, but you only have one coin. So you can take that same coin and flip it multiple times. Right? The idea is what transformation we should do if it is biased to begin with. Disregarding this question, what about the content in general? Is everyone okay with that? Are there questions about this material? Right, so they're already content shared with you on Canvas for quizzes. Let me just share another screen. The programming notebooks that you want to attempt for today essentially correspond to this basics of classical systems. Zoom in for a bit. Assuming you've already downloaded the Jupyter notebooks, this is something you should have access to. It was already reviewed in the introductory session. The tutorial is already there in Abu's talk and also on the YouTube channel. Notebooks that you want to attempt or review essentially correspond to these ones today. And that's essentially corresponding to the material that we discussed already. Each of these have additional videos as well that you can review, and smaller programming questions as well. So coin flipping. So you've got small kind of programming exercises for which you want to write down the program. If you are stuck on some of the programming details or are new to it, you've got this link to check the solutions as well. For links to all these notebooks, I recommend you go back and review the tutorial from the first day of lecture, and the links to it are also on YouTube. You've got kind of the link for downloading them. Should be on Discord as well, on Canvas as well. The first few kind of programming exercises are simply leading you to building these simulation of coin flip experiments to get a better feel of these kind of results and get to probabilistic representation of information, probabilistic operation to probabilistic operation. So the general recommendation, as I mentioned earlier in the discussion today, is first you work through these programming exercises a bit to gain intuition about what's happening, Canvas quiz, rather than doing the Canvas quiz directly to begin with. People can do that, and people have been known to do that, but the ideal learning experience, recommended learning experience is you work through these notebooks and then move to the quiz. This will become more necessary as we move to the quantum part starting from tomorrow's discussion, where the real purpose of these exercises is to gain intuition about what's happening in a given quantum experiment or setup. And with that, I think I'll pause for today because we're already over time. Questions, issues, concerns? There might have been questions that I've missed. Some of the where can I find this kind of questions, I think you can already look up on Canvas code. Thank you. Which folder? So if you go to your, should be, so when you download the bronze folder, it should be kind of the main mean, just open up the folder and you should see this entire list of notebooks. It's called the Start notebook, right? So the file name is Start. I'll stop sharing now. Thank you. Malu, it's all yours.
Yes, thank you very much, Jibran, for the lecture about classical systems. I think we all knew what a bit is, 1, 0, but with the matrices, you added some additional dimensions. Today, we started with the WOMANIUM quantum spotlights, discussed everything from quantum sensing with light, the prisoner's dilemma with quantum, or quantum computing applications in finance. I hope you got inspired by that, and then you got a solid basis by Jibran, followed up the transition into quantum tomorrow. As Jibran explained, for today, there are Jupyter notebook and repeat everything, do the homework, and then there is a Canvas quiz, the assignment. Looking forward to seeing you tomorrow again, same time, with, skip to the slide, 2 great presentations. We will start with William Oliver, the director of the Center of Quantum Engineering, the Massachusetts Institute of Technology in the US. He will give an introduction to quantum computing, starting again from the history and the qubits all the way to where we are now, how a quantum computer is built, and what the applications are. And then Jibran will continue with bronze about quantum systems and the basics of quantum program. Thank you very much all. Keep on discussing on Discord, do the Canvas quiz and Jupyter notebooks, and we will see you all tomorrow again. We will close the session now. See you tomorrow.